Today we will learn about increasing and decreasing functions and how we can use derivatives to learn about increasing and decreasing functions. To understand its concept, let's consider that we do have a linear function, and this function is f of x is equal to 2x plus 5. So it is a linear equation. So its graph will look like a straight line. For example, we have x-axis over here, which is our independent variable. And we have f of x along the y-axis. You can also call it this y, so which is dependent variable. So now this graph, it will look like following, that a straight line which is actually crossing the y-axis at 5. And this straight line, it has a gradient of positive 2. And if we look at this straight line, we can see that with increasing the values of x, values of independent variable, this function is also increasing. So this is continuously going up. So it means that this function is actually an increasing function. So if this is an increasing function, then what is the meaning of the decreasing function? Let's consider another equation, which is again the straight line equation. And this equation is, let's say, negative 3x plus 7. So this is also a straight line, and we can see that in this, that this line is actually intercepting at a positive 7, the y-axis, and negative 3 is the gradient of this function. So we can actually have its graph. It will look like this here. Now you can see that what is happening, that this function is decreasing with increasing the values of independent variable, which is x. So it means that we can actually find a function increasing or decreasing with its gradient. This decreasing function, it has its gradient, which is negative 3. So this one is a decreasing function, decreasing function. Now, were two things that we actually need in our mind, that we need to actually decide about the decreasing and increasing function with increasing independent variable x and the gradient. So this simple information that we can actually also use with derivatives, because we know that the derivatives are actually the gradients. For example, in our this first function here, the gradient of our this function f prime of x, the derivative of 2x is 2, and it is actually greater than 0. And for this second function, its derivative is f prime of x is negative 3, because the derivative of negative 3x is 3, and a derivative of a constant term is 0. And this one is smaller than 0. So now we can say that a function f of x, let's change the color. So we can say that a function f of x is increasing on the interval a to b values of our independent variable if f prime of x, which is first order derivative of the function f of x, is greater or equal to 0 for all values all values of x within this interval. So you can actually also say that for x greater than a and smaller than b, so within this interval. So similarly, we can say that a function f of x is decreasing with the interval on within the interval a b if our first order derivative is equal or smaller than 0 for all values of x smaller than b or greater than a. So this is actually the simple concept of increasing and decreasing functions and the rule of differentiation to identify increasing and decreasing functions. Now the question is that here we simply looked on our simplest functions that are linear. What about higher order functions? So for that, let's consider second order like a quadratic and the third order like a cubic and higher order functions. Okay, let's consider a quadratic function, which is f of x is equal to x square plus 2x minus 3. The graph of this function will look like following, that it is a parabola and it's a positive parabola. And this parabola, it should look like this, that it is actually having the y-intercept of minus y. So we have x-axis here, and here we do have f of x, or you can also call it y. So now you can see that if we are increasing our x value, then from this positive infinity, this number is decreasing, and it is decreasing up to the turning point, up to the turning point. So up to turning point, what is happening that this function is a decreasing function. What above this turning point, this function is an increasing function because the value of this function is increasing with a further increase in the x values. So then this parabola has both natures, the decreasing function and increasing function. So below the turning point, this parabola is a decreasing function, but above the turning point, this parabola is an increasing function. So now we can utilize the knowledge of derivatives to find out that in what interval this function is a decreasing and in what interval this function is a decreasing function. So now we take the first order derivative of this function f of x with respect to x. Derivative of x square is 2x, and the derivative of 2x is 2. So now here we have actually the first order derivative. Now we can see that what could happen, that if we take this 2x plus 2 is greater or equal to 0. So in this situation, you can very easily see that this is x plus 1 is greater or equal to 0. Now, from this, you could see that this x is greater or equal to negative 1. So this information actually tells us that this function is actually because this is greater, so then it means this is actually the increasing function. So this function will be increasing function from for the values of x that are greater than -1. So our interval will be that -1 to infinity. So this is actually the increasing function condition. What? For the interval below this, meaning that from negative infinity value of the x variable to -1, this function is a decreasing function. This function is a decreasing function. Now, from this actually given function, you can also test it because we know that what is the x variable of the turning point. The x variable of turning point is x is equal to minus b over 2a. What b is the coefficient of the x variable, that is 2. So we will have -2. The a is the coefficient of x square term. So that is 1. So 2 times 1 is 2. -2 divided by 2, that is equal to -1. This is actually our answer of the x coordinate of the turning point. As we look from this picture, that this function is a decreasing function up to the turning point, and it is an increasing function above the turning point. So this is what we also have in our actually answer of the derivatives. Now let's consider that we do have a negative x term, meaning that we just flip this parabola. Now we have our new quadratic function f of x is negative x square plus 2x, and we have positive 3 as well, which will be the y-intercept. So then this parabola, it will actually look like something like this over here, meaning that we have flipped it and the y-intercept is a positive 3. Then now we can see that in this condition, our parabola is increasing function up to the turning point and a decreasing function above the turning point. Now we again test it with our actually the knowledge of the derivatives. So first order derivative of this function is very simple, that you can see it is equal to -2x plus 2. So now if we actually check the condition for the increasing function, then you can see that this f of x is greater or equal to 0. So this means that -2x plus 2 is equal or greater than 0. So negative x plus 2 is greater or equal to, sorry, this must be positive 1 is equal to 0. So it means negative x is greater or equal to -1. Now to remove this negative sign, we need to divide it by -1. Then this actually the sign of inequality will flip. So it means that x is smaller or equal to 1. So now our actually new condition or interval of increasing function will be following, that this function is actually increasing function for the values of x smaller than 1. So the interval -infinity to +1, our function is increasing function. Now, we can also see that here above this interval, which is actually 1 to positive infinity, what we do have, we have a decreasing function. We have decreasing function. So this is actually exactly opposite to our this positive x term or positive parabola. And here you can see our actually the answer through the derivatives is exactly what we can see in this picture. So we actually here understood that how we can find the increasing function, a decreasing function, and within one function, the interval within a function is increasing and decreasing. Now, what we can do, we can actually go to the higher order graphs, and there I would like to show you the graphs, real graphs, and where we can actually see what is happening to the increasing interval and the decreasing intervals. Okay, so let's understand our this increasing and decreasing functions using derivatives. And for this, we use this online resources that called Desmos. So this is a Desmos calculator. So you can use it to learn about graphs. And here, for example, we give a graph of y is equal to, let's say we have a higher order graph, which is order 4, x power 4 minus 2x square. Let's see, we have this graph. So here you can see some very important information about this graph, that what is happening, that you can see with on this software. You can actually also get the very easy information about their turning point, about the points where they are crossing the x-axis, y-axis. X-axis mean the roots, and then here you see what is happening, that if we are increasing the x value of this function, then first this function is decreasing up to this point, -1, that is the value of the x coordinate, and then it is increasing function up to the origin, and above the origin to a +1 value, this function is decreasing, and again it is an increasing function. So now what we can do, we can also have a look at the graph of its first order derivative. And the first order derivative, you can see that must be equal to, that y is equal to x power 4. Its derivative is a 4 times x power 3 and negative 4x. That is the derivative. Now, if we zoom it a little and we have a careful look over here, that what is happening, that our actually this graph is actually the gradient graph, meaning that up to -1, the value of the gradient is negative. So if the value of the gradient is negative, then it means our function is a decreasing function. And then from -1 value of the x to 0, our gradient you can see is positive. So it means that the gradient of the real function is actually positive. Then where it is 0, we have actually then our turning point, and above it, the gradient you can see is negative. So our gradient graph actually shows it that it is negative up to point 1, where our actually this you could see the function changes its gradient from negative to positive, and afterwards it is positive. So here, if for example we solve it with our inequalities, then we can have the following equation, that the 4x cube minus 4x, let's say it is greater or equal to 0, then 4 is a common, and we can say this is x is common. So x square minus 1, that is actually in the form of factors, what this quadratic factor can be changed into the linear functions using the formula of square of difference of two squares. So this will turn into x, and x minus 1 into x plus 1 is greater or equal to 0. So Now, this zero condition, we can very easily understand from these three factors that we do have actually our, you can say, one of the turning points at x is equal to 0. So then here, if our x here is less than 1, smaller than 1, what it is still positive, meaning that uh, x is actually changes from 0 to negative 1. When x is 0, everything is 0. When x is going from 0 to positive 1, let's say positive 1. So then at positive 1, our this second factor, it will turn into 0. So it means that until this x value is positive and smaller than 1, that this product of three factors, it is actually giving us negative value. So then it would not be followed here. So it means that this x from 0 to positive 1. So 0 to positive 1, it is not an increasing function, it is a decreasing function. So then you can see that if, for example, we change x from a 0 towards negative 1, so then if it is negative 1, we will have here negative term, and here we will have a positive term because we have a positive 1 here. And then this x is actually negative, so negative times negative, answer will be positive. So then this inequality will be true. So it is over here. So within this interval, we have increasing function from 0 to negative 1. Now, if, for example, x is smaller than negative 1, smaller than negative 1 means that it is moving towards negative 2, negative 3. So then, of course, this first factor is negative, second factor negative, third factor is also negative. So negative times negative positive, positive times negative is negative. Then our actually this inequality is not true. Then it means that our gradient is negative, as you can also see here in the graph, and we will have decreasing function. Okay, and for x greater than positive 1, then we will have all positive values, and this inequality is true, and we have a increasing function that is over there. So in this way, we can actually use the knowledge of differentiation to find the increasing and decreasing function, particularly for the simpler functions like our linear functions and the quadratic functions. For higher order functions, you can also use the same knowledge in this way. And here with the original graphs, we can actually see with the changes in the functions. Okay, so now here there is also another very interesting information that we can understand with this picture. So you can see that what is happening over here, that when our actually the derivative is equal or greater, meaning that when gradient is positive, we have increasing function. When gradient is negative, we have decreasing function. What if our gradient is exactly equal to 0? Then what does that mean? So here you can understand that when function is changing its gradient sign from positive to negative or negative to positive, it will pass through 0. So it means that when our derivative of a function is equal to 0, that will be a point where gradient is changing its sign. It could be either from negative to positive, or it is from positive to negative. Okay, so this is very interesting and very important. Now we can see in this green function, which is our original function, that it is actually decreasing up to this point, and then at this point where x is equal to -1, now the sign of of the gradient of this function is changing. So you can see that the graph of gradient, it is actually also going from negative to positive. And this x is equal to -1 is the turning point. It is a turning point of the function. That is the turning point of the function. Now, if we go further here at the origin, what is happening? That our gradient is positive, and above this origin, the gradient is negative. Then you see the sign changes from positive to negative, and we do have here again our turning point at x is equal to 0. And then we also have another turning point where the sign is changing from negative to positive, and we have another turning point at x is equal to positive 1. So this information, it tells us that we can find the information of the turning points when we will put this first order derivative is equal to 0. For example, this is actually the first order derivative. So we can say 4x power 3 minus 4x is equal to 0. So 4 is common. So we can say x is a common factor. We have x squared minus 1 is equal to 0. So it's a linear factor, three factors, x plus 1 and x minus 1 is equal to 0. So here we have three values of the roots. So x is equal to 0, x is equal to -1, and x is equal to positive 1. So we have three turning point at these three x coordinates. Okay, so now that what we can actually also see in the picture here, but then there will be another question. The question is that which turning point is maxima and which turning point is minima. So now this actually information we need to find out. So when we say that this turning point is maxima or minima, that means the local maxima or local minima, meaning that, for example, if we say this is our turning point, this central one is turning point number 1. So here you see this is a maximum value to with respect to its surrounding. So from if you move towards the negative values of x, the function decreasing, and meaning the values of the function are decreasing. And if you move further, then the values of the function are also decreasing. So this is actually local maxima. What if we look at x is equal to -1 and x is equal to positive 1? So these are actually the minimum values, meaning local minimum values, local minima. So here we actually can learn about the nature of the turning points using the second order derivative. What is the meaning of the second order derivative? The second order derivative means that we need to take the derivative twice. So here 4 times x power 3 minus 4x, it is first order derivative. It is a first order derivative. Now we take the second derivative. So that derivative will be y. This y is actually the second derivative is equal to 4x cube. Its derivative is 12 times x square, and the derivative of 4x is simply 4. So now you can see here that what is happening. So let me raise this much text over here. So here, this one is actually appeared as a black graph, that is the second order derivative. Second order derivative. Now, let's try to understand our these graphs. So I'm going to minimize it a little more where you can see clearly your second order derivative, which is a parabola because this is x square. And the y-intercept is -4 and it is a symmetric over here. So now what you can see that if we look here at our this turning point, the second order derivative is negative. Second order derivative is negative. Now, if we look at this turning point, then we can see our second order derivative positive, and at this x is equal to +1 turning point, our second order derivative is also positive. So here it means that the second order derivative is positive where we have a local minima, and the second order derivative is negative where we do have a local maxima. Actually, what information are actually we can get here conceptually? You see, what we are actually saying here that our first order derivative is actually zero over here. But the second order derivative is negative. What does this mean? We actually said that a point will be a maxima if the first order derivative, or you can say the gradient of the function, is changing its sign from positive to negative. Positive to negative. Now, to understand it, we consider a straight line. And this straight line is, for example, like this, that now if it is over here, and the second line is over here. So this is line number one. This is line number two. So let's say that this actually the graph is the graph of first order derivative of any function. So now you can see that if we see this derivative, so what is happening that from this point where it is cutting the x-axis, this first order derivative is negative, then it is going to the positive value. Okay. What for this line number two up to this point, our actually gradient is positive and then it is a negative. So you see, we have both conditions here in this graph that when gradient is changing from positive to negative, then you can say the slope of that function is negative because this straight line is representing the line of the first order derivative. Now, to understand the gradient of this straight line, we need to take the second order derivative where the gradient is changing from positive to negative. So positive to negative, so that will be local max. Now, if our gradient is changing from a negative to positive, then we will have a local minima. This is what you can see in case of the line number one, that the gradient is actually changing from negative to positive. And this line is actually the line of the first order derivative of a function f of x. So it means we can see the second order derivative of this straight line is positive, is positive. So if this second order derivative positive, that means the gradient of that function was changing its sign from negative to positive. And here, this will be our local minima. That will be local minima. Now, here you can actually conclude that if our second order derivative, second order derivative is positive, then we will have a local minima. And we actually understand the reason that why it is so, that our actually the gradient of this line number 2 is changing from positive to negative. So if our second order derivative is negative, then we will have a local maxima. Local maxima. So then this is actually the very simple and straightforward understanding of the turning points and the nature of the turning points using the concept of a second order derivative. But now there is also one more very special condition, that if our second order derivative is equal to zero, our second order derivative is equal to zero, then what would happen? So, because here we use the conditions of the straight lines, that is actually very easy to understand. So, it means as we actually looked in case of the local maxima, the sign of gradient is changing from positive to negative, and for minima, it is changing from negative to positive. So, if for an example, I have the first order derivative, and that is like the straight line over here, or it is a straight line over here. And these green lines, these are again the lines of the first order derivative of a function. Now you can see that this line is not changing its sign. It's not changing its sign. Either it is negative to negative, and or it is always positive. So it means that if the first order derivative is not changing the sign, it not changing the sign, or you can say that what is happening, that your function, actually you can see the first order derivative, the value is somehow is changing, value is somehow changing, meaning that there is a trend in the change. What it is positive, meaning that the gradient is going to change its value a little, increasing or decreasing. What it is not changing its sign. To understand it, let me draw a little graph over here, that if, for example, we have a function, and this function is following, that, for example, a function is going like this, and then it is over here. You see, positive gradient, and here it is actually, you can say, changing the trend in its, actually, you can say the gradient. So gradient was higher, decreasing, increasing again. So what? It is still positive. So for an example, that we can say, if we look this graph over here, then the gradient function, it will look like the parabola, and this parabola is over here. So it never crosses the x-axis. So even if this function is like this, and now it is going to the infinity, then you can say it remains always positive. And similarly, if this function is over here, then this actually the first order derivative, it will never change its sign. So it means that in this case, what is happening, the function has a turning point. What that turning point is the change in the trend of the gradient, where the gradient is not changing, the gradient is not changing its sign. In that case, you could see our second order derivative. Our second order derivative in this case that it is a straight line, so that actually can be 0. That can be 0 over here, because this but in this one, the first order derivative is a parabola, but the second order derivative, it will be the, you could say the straight line, but this straight line, it will pass through the 0. So second order derivative 0, or if we have a straight line, then it will also be 0, straight line 0, but for the turning point, it is going to be our second order derivative going to be 0. So then when second order derivative is 0, then we have the turning point that, but that neither the maxima nor the minima. It is the point of inflection. So where the second order derivative is equal to 0, that is our point of inflection. Point of inflection. Good. So this is actually the knowledge of the first order derivative, second order derivative that we can use to understand the nature of functions, and we can actually find the turning points, and we can also understand the nature of the turning points. I hope you understood the basic concepts of increasing and decreasing functions and of finding the turning points and the nature of the turning points. To understand this, we will solve some questions. Here are some exercises, and you can try these all questions here to practice your knowledge that we learned today. And if you cannot understand any question or difficult to solve, just let us know, we will solve it for you.